So yesterday we talked about scatter plots. So in general, how to create them. We talked about how to describe them. So what three things do you need to mention whenever you describe a scatter plot? Strength is one of them. Form and direction, right? So strength, what were we using for strength? Yeah, whether it was strongly following the pattern, whether it was somewhat following the pattern, or whether it wasn't really following it at all. So how wide the dots were scattered around the form. Now that was for a linear form or a nonlinear form. So how well do they follow the established pattern, right? And so yesterday we talked about strong, maybe moderately weak, or weak if we couldn't see any type of relationship at all. When we said form, what were we talking about? The shape of it. And the shape boiled down to what? Linear, nonlinear, or non-existent, right? Unclear. Okay, so nothing that we can really see. And then direction, positive or negative. And how do we determine positive? If x goes up, then y goes up, right? Or the slope. If the slope of the line would be positive, then that's going to be positive. If it's negative, it'd be negative. Okay? So that's kind of what we dealt with yesterday. Now, today, we're going to talk about correlation. So yesterday we said strength. When we look at it, we only had the option of saying, well, it's strong, or it's moderately weak, or weak. Or we could use other words like fairly strong or fairly weak, things like that. We didn't have a way to quantify that. We didn't have a way to show exactly how strong a distribution was or a scatter plot was. So, if we look at these two scatter plots here, and we were kind of analyzing these two graphs. So if we look at these two associations, which one would we probably say is stronger? The second one. They're both what? If I was describing this, what form? They're both linear. They're both positive. Okay? And then if we talk strong, on the left we'd probably say maybe moderately strong, right? On the right we'd say pretty strong. Okay?
Hey, sorry, Rick. Did you have a set of keys here? Teacher came in talking and dropped them.
Nice. Yep. Okay, so on the right we'd say it's pretty strong, right? So they follow the form a lot better. But these two scatter plots show the exact same information. What's different about the two? The scales. When we look at the scales, here we're starting at 40, going up to 160. We're a little bit more zoomed in, right? Here we zoomed out quite a bit. We started at 0, and we worked all the way up to 250 on the x-axis, all the way up to 250 as well, right? So one of the things that you have to kind of keep in mind, and Grace kind of brought this up yesterday. She asked, well, do we have to pay attention to the scales when we're analyzing the strength? And yes, you somewhat do. If we were trying to describe these, if we don't pay attention to the scales, we would assume that one is stronger than the other, when in fact they have the exact same strength. Okay? So one of the things that when you create your scatter plot, or when you are analyzing scatter plot, is to take into account the scale. If you zoom all the way in, you can zoom in so far that it looks like everything's just completely spread out. And it looks like a very weak association. Or you can take that same set of data and zoom so far out that it all looks like it's really tightly clustered, in which case it looks a lot stronger. So you can kind of manipulate what people see based on your scales.
So which one would be the right? Which one's the right?
This would probably be a better, the one on the left would be the better representation, because it actually, when you make a graph, the one thing you should always do is try to utilize your entire x-axis and y-axis. And so you want your scales to reflect that. You want them to account for everything. But here, notice we're going way farther down than we need to. We're going all the way down to 0, and our lowest value is somewhere above 50. And then we're going all the way up to 250, but our highest value is somewhere barely above 150, right? So we don't want to have extra on our scale that's not useful to us, because then that's misrepresenting what we're looking at. So this one on the left would be a better representation, because we have exactly what we need as far as the x-axis and the y-axis to put everything on there. So this is what we would want to look for as far as our display. that make sense? Okay? So, because the scales can manipulate our answers to strength of a relationship, of an association, we were going to find, or we're going to talk about correlation, which is a way to quantify that strength. We can actually get a number to go with that strength. Okay? So correlation, it actually does two things for us. When we calculate the correlation, it measures the direction and the strength of a linear relationship between two quantitative variables. So some key pieces here that you might want to highlight or underline in your notes. The first thing, it measures two pieces of information. It measures the direction. If it's a positive correlation coefficient, so if you calculate correlation and it's positive, that means your association is positive. If you calculate correlation and it comes out negative, that's a negative association. But the next thing it's going to do is give us a value for strength. It's going to give us a way to quantify how strong an association is. And that number won't be affected by the scales. So no matter what graph you're looking at, no matter how far they zoomed in or out, the strength isn't going to change. So we have a way to quantify and know exactly how strong an association is. The other thing, and this is extremely important, correlation measures direction and strength for linear relationships. Correlation only works for linear relationships. If you have a scatter plot that is nonlinear, you would not want to use correlation to determine the strength of your particular association. Okay? The reason for that, and we'll talk about how we know what's strong and what's weak with correlation, but for now, just know that a weak correlation would be something around 0. Okay? So if I had a scatter plot that comes out something like this, okay? When we calculate correlation for this, the correlation would come out to be pretty much 0. This is an extremely weak association. This is basically like a non-existent relationship between the two variables. But if you were looking at this scatter plot, how would you categorize the strength of this scatter plot? That's extremely strong. Okay? If we're looking at the curve that we would have fit on this, those points follow almost exactly that curve, right? So this is an extremely strong association, but my correlation coefficient would have told us it's weak. And that's because correlation does not work with nonlinear relationships. Okay? So it's extremely important that you guys understand that. Correlation only works, it only gives us useful information when we're working with linear relationships. So when they're linear, we can get our direction and strength from this correlation coefficient. Does that make sense? All right. So correlation is denoted with a lowercase r in most cases. So the notation for it, like mean, we had x bar and mu. Standard deviation, we had s and lowercase sigma. Correlation has a notation of r. So when you see that little lowercase r, that's what they're asking for. What's the correlation coefficient? And it's calculated using the following formula. Okay? So I want you to write the formula down. You will be expected to find correlation by hand in a couple instances. Now, it's not going to be an all-year thing. It's not going to be every time we see correlation, we're calculating by hand. It's going to be a couple times, and then we'll be able to do everything in the calculator from then on. But you do need to know what the correlation value, or how to calculate by hand, because you need to know where that correlation coefficient is coming from. Where are these values that we're looking at coming from? So, when we look at this formula, it looks very complicated, right? But what are some things that you notice about this formula? What's that sigma mean? Sum. So this big E looking letter, this Greek letter sigma, this represents the sum. That means we're going to take this value times this value for each of our observations and then add them together. And once we add them together, we're going to divide by n minus 1, our degrees of freedom. We have those degrees of freedom from standard deviation, right? Now take a look what's inside that sigma notation. I have x minus x bar over s. What is that? That's the z-score. X value minus mean divided by standard deviation. So that's the z-score for my x value. And then I have y minus y bar over sy. That is the z-score for my y values. Okay? So in this formula, there's stuff that we have seen before. We have our degrees of freedom. So number of observations minus 1. So however many total observations we have, we subtract 1, we get our degrees of freedom. And then these two pieces inside the formula are the z-scores for each individual variable. So we calculate the z-score for every single x value. We calculate the z-score for every single y value. We multiply them together, so each corresponding x and y gets multiplied together. We add them all up, divide by our degrees of freedom. Okay? And we're going to talk about a way to organize this so it makes it a little bit easier. It's just like a process that you go through to calculate them out. But one of the key things here, we're finding z-scores, right? We did z-scores back with normal distributions. When we calculate z-scores, what units did we put on them? None. Z-scores did not have units, correct? So if I'm calculating z-scores for my correlation, what do you think my units for correlation are going to be? None. Correlation does not have any units. Okay, so when you calculate a correlation coefficient, you will not have any units attached to it. When you get your value, it's going to simply be that value and that's it. No units, no matter what you had in your problem. Okay, so correlation is not going to have any units attached to it. So let's kind of get a little practice working through this formula here. So here's an example. Stats teacher wants to see if there's a strong association between the number of days a student misses and the student's semester grade. So he collected data for 5 of his students. So he kept track of the number of days absent and then the semester grade. We want to find the correlation. Okay. Now, if we were going to create a scatter plot here, which of these two variables would we assign to be the explanatory variable? Number of days missed, the response variable then would be semester grade. So this number of days absent would be our x value, semester grade would be our y. Okay? So each column here represents one student's information. Student 1 was absent 9 days, they finished with a 60% on the semester. Student 2 was gone 5 days, they finished with an 84, and so on. So these values in the columns are attached to each other. They are corresponding x and y values. Okay? So if we want to calculate correlation using that formula, what we're going to do, and a way to organize this, now you can plug it into the formula as you see it and just continue to plug into that x minus mean over standard deviation over and over again, but this is kind of what I do. So I create a table, and I make 3 columns. Okay? Column 1, I keep track of all my z-scores for x. Column 2, I keep track of all my z-scores for y. In column 3, I keep track of the product. So column 1 times column 2. Okay? So, in order to calculate my z-scores, I'm going to need my mean and my standard deviation for both x and y, correct? So, we could do that by hand, but standard deviation takes a lot of work, right? So let's use the calculator instead. So I'm going to teach you how to do this in the calculator so you can find this stuff really easily. So grab your calculators. Okay. Now for right now, we'll go through the process for TI-84s or 83s, if you have those. If you have something else, we'll probably have to, after the lesson, we'll talk through and see if we can figure out how to work it on your calculator. But if you want to find mean and standard deviation for two sets of data, we can do this together as one. Okay? So what you're going to do, your x variables, your explanatory variable, you're going to put those values into list 1. So start with student 1 here and type in the 5 absent values. So put all of that into list 1. Now in list 2, because we have a second set of data that we have to look at, in list 2 we're going to put our y values. Now it's important that whatever order you put the x values in, you put the y's in the exact same order. The first value of x needs to be able to match up with the first value of y. These values are inseparable. So make sure when you put your list 2 in, you put them in the exact same order that you did list 1. So get those two lists entered.
Are you adding this to, like, adding?
You missing a list 2?
First one?
All right, so list 1, list 2, we okay there? Now, the next thing we're going to do then, to get our mean and standard deviations right away, we're going to go to the stat menu, go to the calc menu, so scroll right to the calc, and now instead of one variable that we're looking at, now we're looking at 2 variables, so go to that 2 var stats. Make sure you have list 1 and list 2 if you need to. Okay, and right off the bat, it should give you x bar and sx, right? You should see it on the first screen. So what is x bar? 12. What is sx? 10.1. Okay, what is, and if you scroll down, you should see y bar and sy. So what is y bar? 67. And sy?
21.4.
Okay. How many decimals? Does it go on like for a lot of decimals there?
Yeah.
Give me like two or three decimals.
354.
354. Okay. When you're doing this, you want to try to keep at least 2 to 3 decimals in your calculations. It just makes the things a little more accurate. Okay. So we have x bar and sx, y bar and sy. So what you need to do now is you would need to go through and you would calculate the z-score for each of these x values. So we would take, for the first one, so if we wanted to find our very first one here, we would take 9 minus 12, so x value minus x mean, over standard deviation for x, which was 10.1. Right? So what do we get when we type that in? So what do we get for that first z-score?
7.8.
Make sure and do the 9 minus 12 first, then divide by 10.1. Otherwise, your calculator is going to do a order of operations on you. Negative 0.297. Okay, and again, you can 2 to 3 decimal places. Okay, 3 is probably the best. So negative 2 or 0.297. Okay, so let's kind of speed up the process here. We have 10 values. We just found one of them. So Grace, can you find the value for 5? Eli, the value for 2 here. So you guys are doing X. Sam, find the value for 27. Emma, you find the value for 17 here. So Z-score. KJ, I'm going to have you find the Z-score for 60. Ben for 84. Blake for 93. Larissa for 40. And Hope for 58. And then you guys, kind of in the same order. Lexi, I want you to double check 5. Julia, double check 2. Autumn, double check 27. Danny, double check 17. Michael, do 60. Kristen, 84. Mallory, 93. Kylie, 40. And then we're just going to trust that 58's right. Okay. So everyone calculate their 1Z score. Make sure you're using the correct X or Y. So if you guys were an X value, use the X bar and SX. If you were Y values, Y bar and SY. Okay, so Grace, what'd you get?
Negative 0.693.
Negative 0.693. And do you agree? Okay. Next was Eli at 2.
Negative 0.99.
Negative 0.99.
Yeah.
Julia, you agree? Okay. Sam, you had the next one, 27, so that goes
1.485.
1.485. And who was double checking that? Autumn, you get that? Okay. Emma, you had 17. So if you take 17 minus 12, and then take that value divided by 10.1.
I got that one.
0.495. 0.495. Okay. KJ, you had 60, right? What'd you get? So no. Who was checking or KJ? Michael?
I got negative 0.33.
Negative 0.33. So that's 60 minus 67 divided by the 21.354. Okay. 84, Ben, what do we have?
0.796.
0.796. Kristen got that. Blake?
1.217.
1.217. You agree, Mallory? Okay. Larissa?
Negative 1.26.
Negative 1.26. Okay, you agree? Okay. And then Hope, it's on you. You better have it right.
Negative 0.42.
Negative what? 0.422. Okay. So this would be your process. Okay, you'd find all the z-scores for x, find all the z-scores for y. Okay. Always making sure x's go with the x bar sx, y's always go with y bar sy. So don't get those mixed up. Okay. Now, once we get to here, we just multiply the two columns together. Okay. So you guys multiply the top row, this row here, double check each other, multiply the top row. You guys multiply the second row, third row, fourth row, then you guys do the fifth row as well. We'll make you do double time.
What did you give now?
Okay, so what do we get for the first? 0.098. Okay, second row, what did you guys get? Negative 0.552. Third row, negative 1.20. Okay.
Negative 0.63.
Okay, and then somebody do the last row for me. Negative 2.09. Okay, so negative 0.209. Okay, so z-score for x, z-score for y, multiply the two columns. Just multiply straight across. Now, what we're going to do is we're going to take all of these values in this third column. We need to add them all up. So take these values and add them all together. So 0.098 plus negative 0.552 plus negative 1.2.
I think I timed mine in.
Yeah, 'cause I'm like, I'm not.
Look, hold on a second. You guys were real forward.
I get negative.
0.26 instead of 1.
I get -1.87.
Negative 1.87 here. Oh, this is going to be terrible. I'm going to cross this out. So what should this be?
-1.87.
Negative 1.87. All right, Michael lists it down there. I'm sorry, guys.
Cool.
So negative 1.87. So now, add up the last column again. As soon as you get it, go ahead and tell me.
-3.733.
Negative 3.733. Do you agree with that? Okay, so then the last thing, when I go to find correlation, is take that negative 3.733 and divide by 4. So we had 5 observations, we need to subtract 1 from that, right? So degrees of freedom, we subtract 1. So we're going to take negative 3.733 divided by 4. Negative 0.9 what? Okay, so negative 0.933. So this would be our correlation coefficient. Okay? Now, correlation can also be found on your calculator. And we're going to go through that process now. Like I said, you might have 1 or 2 problems where you do have to do this by hand, and it's always going to be a very small data set. It's going to be something like 4 or 5 observations. So it's not going to be something huge that you're going to be doing this whole process for a lot. Okay? Anything that you have a lot of data points for, go ahead and plug in your calculator and do it with the calculator. Okay? So what you guys need to do here, if you want to calculate correlation in your calculator, you already have the data entered into your list. That's step 1. Step 2 is to go to your stat menu, go over to calc, and I think option 4 for most of you should be, it should say linreg ax plus b. Okay, so go down to that option and select that. Go ahead and enter it until you get the value. Now what you should see is something like at the top of the screen, you see like a y equals ax plus b, and then it has like an a equals, a b equals, right? Does anybody have then underneath an r squared and an r? No, so you guys all have just a and b, right? Okay, so what you need to do is you need to go to your catalog. So for TI 83s and 84s, if you hit second 0, okay, so go to second 0. Now, if you scroll down to the D's, now you can either scroll all the way down, just hold the arrow down and do that, or if you hit the X inverse key, that X to the -1, that'll take you straight to the D's. You're looking for the value, you're looking for diagnostics on. So you're looking for diagnostics on. Okay, so you're going to choose that option. It's going to come up on your screen, and then you have to hit enter again. You have to tell the calculator to turn it on. So now it should say done, right? So once you turn diagnostics on, go back into that linreg function. So go to stat, over to calculate, go down to linreg ax plus b, and now you should see these values here, correct? Okay, so for right now, r squared, don't pay any attention to it. We'll talk about that stuff later. But the one you do want to know is r. r is going to be your correlation coefficient. So on the screen right there, does your correlation come pretty close to -0.933? Okay, so it should. Now it might be a little bit off because of rounding and things like that, but it should be pretty close.
So the diagnostics always stay on, unless you set your calculator.
Yes, so from here on out, your diagnostics will always be on, unless for some reason you have to reset your calculator or erase the memory or whatever. So if on a quiz or a test, you go to find correlation and r and r squared aren't popping up, You have to turn diagnostics on. It means somehow you turned your diagnostics off, but it will not turn off unless you physically do something to the calculator. So those will always be on now. Every time you go there, R should be there. We good with that? Yours wasn't showing up still?
Yeah, mine. No, am I good? Yeah. Yeah.
So when you're at that, so you should have been ready.
You don't want yours? No, I got one.
So you go all the way through and actually. Yep.
Oh.
All right. So keep that value of correlation in mind. -9 or -0.933. We're going to talk about what that means here in a little bit. Okay. Now, here are some things about correlation you have to know. Okay. There's some properties of correlation, and this is going to kind of help us evaluate, like when we talk about strength, how we know whether something is strong or weak. So the first thing, we already have this down in our notes. Correlation measures strength and direction. That's important. It's always two things. Okay? So when it asks on a quiz or a test, it's always two things that that correlation is going to tell us, strength and direction. We use it only for linear associations. Again, something we mentioned before, but it's important enough to repeat. It only works for linear associations. Okay? Has no units. Since it's based on standardized values, which have no units, correlation will not have units as an overall. Okay?
Is there any difference between the words association, correlation, and relationship? Are they all just like interchangeable?
Yeah, association and relationship mean the same thing. So if we're talking about what, like, describe the association or describe the relationship, that's the exact same thing. If we say correlation, though, correlation does have a specific meaning different than association and relationship. So the relationship, the association, that's what we're trying to describe. The correlation is a measure of that association. Does that make sense? Okay. So has no units. Never put any units with your correlation. We already talked about it. It's denoted with a lowercase r. Here's the important stuff. Okay? So here's the stuff we have not mentioned yet. When we talk about correlation, your correlation must be a number between -1 and +1. If you get a value outside of -1 to +1, you did something wrong. So on a quiz or a test, if you're calculating by hand and you get a correlation of 1.6 or -1.2 or -3 or something like that, you know you did something way wrong. Okay? Correlation has to be a number between -1 and +1. Now, as far as strength is concerned, the closer we are to +1 and -1, so the closer we are to 1, the stronger our linear relationship is. So if we get a correlation of exactly 1 or a correlation of exactly -1, that means my data lined up perfectly. It all falls on an actual straight line. Any variation from that straight line then is going to start to lower that correlation value. So 1 and -1 mean very strong associations. +1 means a positive linear strong association. -1 means a negative strong association. If you get values closer to 0, the closer to 0 you are, the weaker your association is. So that could be on the positive or negative side, it doesn't matter. The lower your correlation coefficient, the weaker the association is. Okay? And the good news for correlation, if you're plugging into your calculator and you accidentally mess up and you put y in list 1 and x in list 2, it's not going to matter. Correlation comes out to be the same regardless of the order of your explanatory and response variables. So you should always get the correct value regardless of which order you put them in. Okay? So, going back to our example that we just talked about, we got a value, a correlation coefficient of -0.933. So what does that tell us about the relationship between number of days absent and semester grades? It's a negative association and it's very strong. Okay, it was very close to -1. So there's a very strong negative association between number of days missed and semester grade. You okay with that? All right. Next thing, being able to identify strength off of a graph. So basically measuring correlation based on what a graph or a scatter plot looks like. Okay? So we know that the closer to 1 we are, the stronger the association has to be. The closer to 0 we are, the weaker it has to be. Okay? So what we want to do here is we want to try to match up. Here's 6 correlation coefficients. Here are 6 graphs on the right. We want to try to match them with the correct values. So take about a minute here and see if you can match up those values. Just think to yourself, which correlation coefficient should go with which graph? Okay, so let's just kind of run through these. Correlation of 0. Which of those 6 graphs is probably the one that matches with correlation of 0? Top left. So correlation 0 is going to be top left. If we're looking at that one, there really is no form to it. We don't really see any sort of line or curve or anything in there. Okay, it's just a random scatter of dots. We're going to be very close to 0. What about negative 0.3? Okay. Should be top right. So if we're looking at that one, now we can somewhat see maybe a negative linear association, but it's still really not that clear, so it's going to be a pretty low value of correlation. Okay. What about the one below it? How about this middle right? Which one was that going to match up with? Probably negative 0.7. So out of all of our choices, now we're starting to see it really start to tighten up. It's starting to follow that form a little bit better, right? Still the negative direction, so we still need to have a negative correlation coefficient, but we're getting closer. What would that bottom right match up with? The negative 0.99. So this one is almost in a perfectly straight line there. The points are really closely scattered or tightly clustered around that form. Okay? On the left then, 0.5 is going to go to that middle left, 0.9 is going to go to that bottom left. Okay? Back up on me yet, we still got some time. Alright, so one of the things you need to be able to identify. So given a graph, you might be asked, what would the correlation coefficient approximately be? You have to be able to give a fairly decent answer, how close you can get to the actual value. So you need to be able to look at the two things. You need to know what a correlation coefficient would look like as far as an association on a scatter plot. So how would those line up according to that correlation coefficient? Okay? So extremely important stuff there. Now, some other things with correlation. Okay? 3 things before you do anything with correlation. First, you need to make sure you're actually dealing with quantitative variables. Okay? If you don't have quantitative variables, you can't do correlation. It only works on quantitative. You need to make sure that you have a linear association. If your association is nonlinear, correlation is useless to you. It's not going to tell you anything worthwhile. That's what you have to look at the scatter plot. So you have to look at the scatter plot. If it looks linear, you can do correlation. If it looks nonlinear, you don't even bother with correlation. Okay?
So if you only use it if it's like linear, how would you ever get 0?
If it's a weak association. Like if you just see a random scatter, there's not really a form, but you would almost never see a 0 correlation. You're going to see something with it, in which case there's some sort of linear look to it. It's just a very weak look, so they'd be randomly scattered. 0 is tough to come by. Usually it's when people use correlation on a nonlinear and don't realize it. That's when you're going to see the zeros mostly. Otherwise, you're really not going to see exactly 0. Okay? And then the last thing, outliers. If you have outliers in your data, that is going to greatly affect correlation. Okay, and we're going to talk about how to account for that here in a second. But these are the 3 things you need to kind of look for before you even bother working with correlation. Do you actually have quantitative variables? Are they in a linear association? Are there any outliers to be concerned about? Okay, so last thing here. Correlation is not resistant, meaning it will be affected by outliers. So it is not resistant. It will be affected by outliers. So here we have a scatter plot. When we evaluate the association, we get a correlation coefficient of 0.634. Okay? Now, if we look here, we do have a linear association. So we're okay there. But we notice that there's a couple points maybe that fall a little off the beaten path. So here we have most of our data here. This one falls off to the side there. This one maybe even falls a little bit out of the pattern as well. Now if we remove those, so we take those values out, now our correlation goes from 0.634 up to 0.783. Okay, so it's making it a stronger association. When you have outliers, the way to handle it is to calculate correlation with the outlier in and calculate correlation a second time with the outlier out. Now the good news is you will never have to do that by hand. If I'm having you calculate correlation with outliers in there, you're going to be doing it in the calculator. So all you're going to do is do it with all the data in, and then go into your list and delete out the outliers and recalculate correlation on the calculator. And you're going to report both values. Okay? So then people can look at it and make their own informed decision. Which correlation do I want to go with? All right?
So both of those will be your answer?
Yep. So you'd have 2. R should never be used alone. Correlation. You never just say the correlation is this. You always have to have a graph. So you always need to report correlation with an actual picture of the scatter plot. So that could be a hand-drawn scatter plot, or it could be a sketch from your calculator. Okay? But you need to have a graph that goes with it so people can see the correlation coefficient and see the linear nature of the association. Because you could report a correlation that looks really strong, but it's a non-linear association. So the correlation's meaningless. So people can try to mislead you with things like that. So you have to make sure that the graph comes along with correlation. And then last, again, cannot stress it enough. Correlation is useless if the association is nonlinear. So do not use correlation if it's curved. Okay? So here is your assignment. Work these problems out this weekend. Okay? You do not need to get every single one done, but you do need to get at least some of it done so you know whether you have questions or not for Monday.
What? I like it.
Turning that thing on the calculator, does it affect anything else besides giving the R?
No.
Okay.